Different from permutations, we have what's called a combination. So a combination is an arrangement of objects in which the order does not matter. So we no longer need to think about the order when we think about a combination. So this would be something like the number of ways in my class of 20 students, I could select a group of 3 students to be on a committee where they work with the principal on something. So these are just choosing rather than arranging in order. So here's an example. The Library of Science Book Club offers 3 free books from a list of 42. How many possible combinations are there? So again, order is not important, so this is a combination problem and not a permutation problem. There are 42 times 41 times 40 ways to choose the 3 books, but that is thinking about it in order, right? Because I have a first, a second, and a third. And then the 3 books I choose, or the way in which I choose them, can be arranged in 3 times 2 times 1 ways if I think about the order. So this all culminates in another formula for us. So if we have the number of combinations of R objects chosen from a set of N objects, where N 0 is less than or equal to R, which is less than or equal to N, is denoted by this little c, N, big C, little r, and I would read that N choose R, or N combine R. And it's given by taking the number of permutations of permuting R things from N objects, and then dividing out the number of ways to permute those R things with each other. So basically taking out double counting. So if I have again with the alphabet, if I were to choose 3 letters from the alphabet, instead of permute them, I would want to say that ABC is the same thing as BAC because it's the same group of letters. So I would have to divide by the number of ways to arrange 3 things to keep from double counting all of those. So we can simplify the formula. N factorial over N minus R factorial divided by permuting R things, just R factorial. We can simplify it, and this is the formula that you will likely be using the most. N factorial divided by R factorial times N minus R factorial. So if we go back to this example that's offering 3 books from a list of 42, then we will have N choose R would be 42 books, choose 3 of them. We have 42 factorial divided by R factorial so this is our R factorial, and this is coming from N minus R factorial, which was 42 minus 3 factorial. And then we can simplify it out and calculate and see that there are 11,480 ways to choose 3 books from a list of 42. Another combination example is at the beginning of the first semester of a math class for elementary school teachers. Each of the class's 25 students shook hands with each of the other students exactly once. How many handshakes took place? So this is actually a combination problem because we're essentially finding the number of ways to pair 2 people together. A and B shaking hands is the same as B and A shaking hands, so the order doesn't matter. So we can find the number of handshakes that took place by saying 25, choose 2. So the number of ways we can choose 2 people from the set of 25 when those 2 people are not repeated, right? You're not going to shake hands with yourself. And that would be 25 factorial over 2 factorial, 23 factorial. Again, the 23 factorial coming from 25 minus 2 factorial. And then working it out and getting 300. All right, so if we think about an example where we have 12 girls and 10 boys in a class, we might want to know how many ways can a committee of 5 with 3 girls and 2 boys be chosen. So we can think about how many ways we can choose 3 girls and how many ways we can choose 2 boys. The number of girls, or the 3 girls can be chosen in 12 choose 3 ways, and this comes from having 12 girls in the class and we're choosing 3 of them. So if we want to choose the 2 boys, we would have to choose 2 from the 10 boys in the class. So we would use the fundamental counting principle to just multiply those number of ways together. So there are 12 choose 3 ways to get 3 girls. There are 10 choose 2 ways to get 2 boys, and that would come out to 9,900. So we could turn this into a probability question. So instead of just asking how many ways are there to make a committee of 5 students, 3 of which are girls and 2 are boys, we might say, what's the probability that a committee of 5 chosen at random from this class consists of 3 girls and 2 boys? So to do this, we would have to find the total number of committees of 5 students. So this would be 22 total students in the class, choose 5 of them, and again, we could get this number by 22 factorial over 5 factorial, 22 minus 5 factorial, and working it out to get 26,334. So we know that there are 9,900 ways to get a committee of 3 girls and 2 boys. So knowing that there are 26,334 total number of committees that could be chosen, we can find the probability of the number of ways of choosing a committee with 3 girls and 2 boys over the number of total ways of choosing the committee. So 0.3759-ish probability, or about 37.5%. We might also want to ask, in how many ways can the committee of 5, if we're going to choose it from the class, have no boys at all? So this would be just choosing 5 girls and 0 boys. So to choose 0 boys, we would just do 10 choose 0, which would be 1. There's only one way to choose nothing from 10. And then to choose 5 girls, we'll do 12 choose 5. So 12 factorial, this number again is coming out of 12 factorial over 5 factorial, 12 minus 5 factorial. And so we get 792. Then we might ask, okay, so say we chose that this committee at random, what's the probability that it was all girls? And so again, we know the total number of possible committees is 22 choose 5, or 26,334. And from part C, we know that there are 792 ways to get a committee of 5 girls. So the probability of getting an all-girl committee would be 792 divided by 26,334, or just around 3%. So it's a lot less likely that you would get a committee of all girls if you chose it at random. And that is all I have for you today. So good luck with your homework, and let me know if you have any questions.